So it's my honor today to introduce David Lindell to MERL. David received his PhD from Stanford, and then, as we were just talking about, he had the foresight to get a job in Canada, where he is currently an assistant professor at the Department of Computer Science at the University of Toronto. I've admired David's work on single-photon LiDAR and non-line of sight imaging for a long time. Uh, when I was a postdoc at Stanford, he also started working on implicit neural representations. So some of you might know him from the Sirens paper using sinusoidal activation functions. Just a few of the many awards David's PhD thesis got an ACM SIGGRAPH Outstanding Dissertation Honorable Mention. And more recently, he got the MERL Prize at ICCV in 2023. And I think that's some of the work I'll talk about today. So without further ado, welcome, David, and the floor is yours.
Great. Yeah, thanks for the introduction. Thanks for having me. And I'm excited to be able to talk about some of our work we've been doing over the last couple of years at U of T, and to talk about imaging dynamic scenes from seconds to picoseconds. So now as I share my screen, you should be able to see the slides, but I realize I don't see any of you. So if there are questions, maybe Josh can interject and just stop me. I'll also try to pause throughout so people can ask questions if there are any. So I want to start off by showing you this time scale. This is the entire range of time scales that humans have observed in the universe. It goes from something like the exasecond scale all the way down to the attosecond scale, where the age of the universe is around 100 petaseconds or so. And the smallest timescales that we've been able to observe are near the attosecond scale. And the Nobel Prize in Physics in 2023 was awarded to these scientists for the invention and invention of applications of the attosecond laser. And using the attosecond laser, we can now image at these incredibly minute timescales. Attosecond timescales are basically the timescales at which electrons are moving around atoms and molecules. And so we can actually now capture electron dynamics using these ultra-fast lasers. And in between these two extremes, we have this huge expanse of time. And inside of this expanse is basically every physical phenomenon known to man. So all of human existence occurs within a span of around 6 trillion seconds. I'm around 1 billion seconds old, so you can figure that out in years if you wish. The protein folding takes around a microsecond. The fastest transistors that we can make can switch on and off in around a picosecond, 10 to the minus 12. And if you compare this huge expanse of time to the range of timescales that conventional cameras can capture, there's actually an enormous disparity, of course. So our current cameras are limited to just capturing small slices of this temporal spectrum from timescales of seconds down to perhaps microseconds. The fastest commercially available conventional cameras can operate at speeds up to perhaps 1 million frames per second. And that's fast enough to capture a speeding bullet crashing through an eggshell, like I'm showing you in this video. Okay, but as we try to move beyond a million frames per second, we hit a brick wall of sorts, and there's a kind of phase transition that occurs. So there are technologies that can image at speeds faster than that, such as depth cameras, LiDAR systems, or street cameras or interferometric techniques. But what you'll notice is that they capture a relatively small range of timescales. And I would characterize this by what I'll call the temporal dynamic range of these systems. That would be the ratio of the maximum resolvable frequency to the minimum resolvable temporal frequency. And usually this is about around 1,000. So you can capture events with femtosecond temporal resolution, say using a street camera, but only for a duration of around a picosecond for various reasons. And what we're after is to create an ultra-wideband imaging capability where we can image across timescales spanning many orders of magnitude, for example, from seconds all the way down to picoseconds. And so I'm going to talk about ultra-wideband imaging in 2D, and then I'll also, in the second half of the talk about how we can perform what I'd call light speed neural rendering, or to visualize ultra-fast events happening in 3D. So what can we capture with an ultra-wideband camera? Here's a scene. This is captured with an iPhone camera, so like a conventional camera. Has a fan that's spinning, and there's also laser pulses that are being fired at this scene. They're propagating through it, although they're too faint to be seen by this iPhone camera. Now, if we capture this scene with our ultra-wideband camera, we can capture it once, and then computationally, we can play it back at any time scale that we wish, from hertz to gigahertz frame rates. So that's what I'll show you now. So at the scale of kilohertz, we see that fan blades start to slow. As we push into hundreds of kilohertz or even megahertz, you start to see the pulses of light from the laser. At 10 billion frames per second, you can actually see the motion of light and the wavefront sweeping through the scene. And at 250 billion frames per second, 250 gigahertz, light slows to a crawl, and you can see the fan blade frozen in position. So again, this is a scene captured once and then computationally played back at different time scales. So this basically overcomes this brick wall. This capability overcomes the brick wall that I showed you before. So why were previous techniques limited by this barrier? Where does it come from? Well, as you push to faster and faster imaging speeds, you're basically shrinking your exposure times to be shorter and shorter and shorter. So to capture enough light within a single exposure time to form a clean image, you start to require intractably bright light sources. The illumination sources would have to be so bright at picosecond or shorter timescales that you'll basically just start to fry everything that you're trying to capture, just disintegrate. So modern ultra-fast imaging systems operate on a different principle, which was pioneered by Doc Edgerton, who's a professor at MIT, and performed the seminal work on high-speed imaging. In particular, he pioneered two innovations that are still used in ultra-fast imaging systems today. The first is the high-speed flash, and the second is precise synchronization of your detector or the scene that you're capturing with that high-speed flash. So I'll let Edgerton explain this principle, and I'll play a video of him doing that. So hopefully you can see the video and hear the audio on the next slide here.
The principle of this high-class gadget is a light that flashes on and off at variable speeds. Through this invention, you can examine machinery in motion. Here, a common electric fan is used in a simple demonstration that even I can understand. Or can I? Anyway, when you direct this light on a fan and synchronize the light flashes to the revolutions of the fan, the blades appear to be stationary.
So here's the principle. Basically, by synchronizing the light source, in this case with the scene, you can freeze the motion of the scene, and that allows you to expose your camera or imaging system for as long as you like to collect enough light to form a clean image. And in the intervening years since Edgerton pioneered these principles, they've basically been scaled up and deployed to considerable effect. So this is a video captured by Velton et al. At MIT in 2013 that captures light propagation, in this case, a light pulse propagating through a Coca-Cola bottle at a frame rate of around 500 gigahertz. And so how does this work? They synchronize the emission of laser pulses into the Coca-Cola bottle with the imaging system, allowing them to freeze light at a particular time. So there's a fixed offset between the emission of the laser pulse and the capture of an image in this case. And that allows them to repeat this measurement procedure over and over and over again. The scene is frozen and they can accumulate enough photons to form a clear image. So this is actually, we replicated that experiment in our lab. You can see the individual frames that are captured by such an imaging system. And you can create then a video by just shifting the synchronization slightly between the illumination and your camera, capturing light frozen at different positions, and then stitching these frames together into a video. So this experiment by Velton et al. Basically scaled everything up. You have synchronization now at the picosecond level. You're strobing your light much, much faster than Edgerton ever did, at 75 megahertz in this case. And although this allows you to capture ultra-fast events, it's really Edgerton's principles are really a double-edged sword. So it also means that you can't simultaneously capture fast and slow events. So in this case, you can't capture events that are much slower than the repetition rate of your laser pulses, of your strobe. So why does that happen? Here's another example that I think shows this more clearly. This is a photo captured by Edgerton. He left the exposure of the camera he left the shutter of the camera open, and then he strobed a light. And as this person swings the golf club, you can see that the golf club is resolved clearly. And that's because it's moving faster than the strobe. But what about the torso of the person? This is all blurred out because it's moving at a slower rate than the strobe light. So since the motion is slower, it gets blurred together or averaged out during the long exposure time. And we see a similar type of phenomenon in an ultra-fast imaging system. If we apply that, in this case, to the same captured scene I showed you at the beginning of the talk, if we use this form of synchronized imaging, the fan blades are blurred out because we're capturing this event over and over and over again. And during the exposure period, the fan blades are moving slowly, and so there's this kind of a form of motion blur that happens. In contrast to what we see in ultra-wideband imaging, where we can resolve both events at both time scales clearly, the wavefront propagating through the scene and the fan blades being frozen in position. Okay, so let me get into the nuts and bolts of how this works. So first, let me start off with a conventional view of video acquisition. So the conventional wisdom is that a pixel's time-varying flux or time-varying intensity recorded by an imaging system is some continuous function. And the only thing that we need to do to record faster and faster video is to just sample this function more finely by running our system at a faster frame rate. Of course, this conventional view of video acquisition starts to break down as we move to faster and faster timescales, because in fact, the incident intensity of light is not a continuous function, and light is made up of individual particles called photons that arrive to our sensor in a discrete fashion, stochastically and asynchronously. And in general, these photons could be arriving from maybe one light source. That light source could be modulated, and depending on the intensity of the light source, the photons will arrive at a time with a time varying arrival rate. And in the general case, we could have many different light sources. They could all be have a different form of time modulation, and our sensor records simultaneously photons arriving from all of these different light sources. And so really the best that any sensor could do is to timestamp the arrival of each and every individual photon and record that timestamp with respect to some absolute clock. So then once you have the timestamps of all of these arriving photons, what you'd like to do is try to estimate the underlying continuous function of the incident intensity of light onto the sensor. Unfortunately, there are devices that record such timestamps. They're called single-photon detectors. One type of single-photon detector is a single-photon avalanche diode, or SPAD. And SPADs, well, the SPAD that we have can record around 2 million photons per second with a very precise temporal resolution, down to around 16 picoseconds or so. And so given the timestamps, the question is, what can we infer about the underlying continuous intensity or flux incident on the sensor? And it turns out that there's a deep and very interesting mathematical connection between these two quantities, the discrete timestamps and the continuous flux. In particular, they're related through this equation. So this equation relates what's called the counting process, n of t, to an integral of phi, the flux, over time, plus something called m of t. So the counting process is just a function that increments by 1 every time you detect a photon. This integral is just the integrated flux function up to time t, and m of t is what we call martingale noise. So this is a kind of stochastic process equivalent to white noise. One example of which would be an unbiased random walk. And this equation follows from some key results in stochastic calculus. We also derive it in our paper, but it follows also directly from something called a Dube-Meyer decomposition. Okay, and what is m of t? What is this martingale noise? This is exactly the difference between the integral of the flux function up to time t and the counting process. Okay, so I'm not going to go through all the math in this talk today, but if there are questions about it, I can certainly revisit that afterwards, or we have all of the derivations in the supplement of our ICCV paper. But let me just skip to the punchline here. And if you massage this this stochastic integral equation I showed earlier, you can get it into this form, where we have the sum of a function p evaluated at the timestamps, and that turns out to be equal to an inner product of p and the flux function plus noise. So you can think of this function p as a function that lets us probe the flux using the timestamps. And if we let p be the Fourier basis functions, we can then estimate a noisy set of Fourier coefficients that characterize the flux function. To do that, we take the sum over the timestamps evaluated at each of the Fourier basis functions. Those give us the Fourier coefficients. And in general, then this gives us a method or an algorithm to map from photon timestamps to a continuous flux through a Fourier transform. So we can probe each of these Fourier coefficients. That gives us the Fourier transform. We can apply some techniques from detection and estimation theory to try to identify the frequencies that don't correspond to noise, take an inverse Fourier transform, and recover back the continuous time-varying flux. And the interesting thing about this is that the maximum frequency of the flux that you can recover is not limited by dead time or a sample rate. It's limited by how precisely you can timestamp the individual photons. So in general, we have this equation where the better your timestamp resolution, the higher the maximum frequency you can recover. And with the SPADs that we use in the lab with picosecond resolution, it's theoretically feasible to recover frequencies up to 31 gigahertz. So you can think of this as a method that takes devices that are extremely sensitive, but conventionally have relatively slow readout rates, millions of photons per second, compared to the fastest photodiodes that can operate at gigahertz rates, but have relatively poor sensitivity. And it turns SPADs into devices that are both ultra fast with gigahertz of bandwidth and ultra sensitive with single photon sensitivity. So let me show you some results, experimental results, and what we can do with this algorithm and with SPADs. So this is a setup where we have a single pixel SPAD observing a single point on this white box. And in this scene, we have a number of different light sources. There's a smart bulb that's sitting above the scene. We have a 3 megahertz pulsed laser that's passing through a diffuser so that some of the light will be directed to this point that we're observing. A 40 megahertz picosecond pulse laser, similarly passing through a diffuser. And we have this raster scanning laser projector. So this laser projector is being projected, the light is being projected onto a diffuser. And so at every point during its raster scan, some of the light will be scattered towards the point that we're imaging. You could think of this as like watching the glow of your projector on the side of on one of your living room walls or something like this. Okay, so then we can collect all the photons with our SPAD, apply our algorithm, and reconstruct the 1D function of continuous time-varying flux. And I'll just visualize what we get back at different time scales. So at the scale of 1 second, we can see this 60 Hertz signal corresponding to the refresh rate of the laser projector. Zooming into tens of milliseconds, we can see the roughly 900 Hertz flicker from the light bulb that was above the scene. At the scale of a few milliseconds, you can see the modulation of the laser projector beam. So this is basically encoding whatever video was playing. At the scale of tens of microseconds, you start to see the pulse trains from the 3 megahertz laser. All the way down to a 1 microsecond time span, we can now identify the pulse trains separately from the 2 lasers. The 3 megahertz pulse laser has a higher peak power. They're about the same average power, so this all checks out. It's operating at a lower rep rate, so you expect the peak power to be higher. And then zooming all the way down to the nanosecond time frame, we can resolve an individual laser pulse whose full width at half maximum is around 120 picoseconds or so. We can even go back and look at that one-dimensional waveform that the laser that we recovered from the laser projector, reshape it into a video frame and try to reconstruct what video was playing. So we can kind of make out that this MGM logo was being played. And if we turn off all the light sources except for the laser projector, we get a cleaner reconstruction and can actually get a bit of a better idea of what was playing. Okay, so we're pretty excited about this technique. We've been working on some follow-on work, and we're also trying to figure out what applications it could be useful for. So one thing that we're excited about is this ability to harvest ambient photons and ambient signals that are operating in the environment asynchronously. So you can detect these asynchronous pulse lasers, and you could imagine perhaps systems where there are light sources operating out in the scene. Maybe there are LiDARs that are scanning the scene. You're not synchronized to them, but you can use those light sources to do 3D reconstruction or navigation, perhaps. This is something that we've been working on and turns out to be possible. You could imagine a type of optical microscope that would allow you to monitor optical behavior from picoseconds to days, perhaps, over very long time intervals. This could be useful maybe for kind of anomaly detection. So we've been working with collaborators in astronomy. They'd like to detect the ultra-fast optical component of fast radio bursts. And you don't know when these bursts are going to happen from deep space. So you have to point your telescope up at the sky, record, and just wait for these things to happen. And then once they happen, you'd like to go back into the data, zoom in, and see what you recovered. And so maybe SPADs and these algorithms could be useful for that. We've also been working on techniques to use these for high-speed, low-light imaging. And there could be other applications in biology or remote sensing that could make use of this technique. So if you have any ideas, I'd certainly be interested to discuss that. Okay, so this takes us to the second part of the talk, but maybe I can just pause here if there are questions.
Yeah, there's one from Hassan.
Hi, David. Just wondering about the video that you were showing. Was that 1 second video itself being played repeatedly, or was the video that basically was the whole video being played?
You're asking about the video from the laser projector.
Yeah,
and if it
the
was repeated
MGM video, and trying to figure out if that is actually being repeatedly played. Like, did you need the repetition of the video, and where the waveform is that 1 second segment of the video for you to be able to reconstruct it?
If I remember, the acquisition was only over 1 second, and so provided that the signal you're trying to recover is slow enough relative to the arrival of photons, you can recover it. There's of course, you could imagine some some transient signals where you don't detect any photons; they only happen once. That's not something that you could recover because you didn't detect any photons from it. But this video was slow enough that we could recover it without it being periodic. Yeah.
Thank you.
Yeah, that's a good question.
Matt has another question.
Yeah, I would like to understand the sensing device a little better. This is a single photon detector.
That's
So
right.
how is the spatial array information of the scene being recovered?
Yeah, okay, good question. So at the time we captured the data, we didn't have a 2D SPAD with picosecond timing resolution. So we basically tried to emulate what you could capture if you had such a device. So the way we captured the video that I showed was to scan the scene, and we had some synchronization of where the fan blade was during every scan, so that we could line up the signals between the pixels, and then reconstruct the flux at every pixel and stitch that together into a video. So this is kind of an emulation of what you could capture if you had a 2D SPAD array.
Okay. I thought it would be something like some kind of spatial light modulator, or just properties of the way the scene is illuminated.
You could similarly, yeah, you could probably get a similar result using some sort of coded illumination, provided that the scene, what you're capturing, is periodic. Otherwise, yeah, you'd run into that issue where if you didn't collect photons from a particular scene point, you can't reconstruct what's happening.
Okay. And could you give us an idea in terms of devices, what's the state of the art? I mean, so each record has a certain number of bits attached to it, and you're constrained by the bus, you're constrained by memory, you're even constrained by the heat of running the device. Like, how long a scene could you capture at picosecond resolution in images?
Yeah, so this is a good question, and it gets to the one of the main challenges, I'd say, with current high-resolution single-photon sensing. It's the bandwidth. So we have in the lab a 32 by 32 pixel SPAD pixel array. You can get out about 250 million photon detections per second over a PCIe interface. But scaling this up to megapixels with picosecond timestamping resolution isn't really possible yet. There are people looking to on-chip compression techniques where you don't read out every single photon detection, but maybe you read out what you call, like, they call it a sketch, or some statistics of the photons that are arriving. And you can do that in a compressive fashion that saves bandwidth. There are, yeah, the current high-speed SPADs are limited to maybe on the order of thousands of pixels because of bandwidth. There are high-resolution SPADs. Now I think Pi Imaging has a megapixel SPAD array, but they can't read out as fast as the lower spatial resolution SPADs. So we have a couple cameras, quarter megapixel SPAD arrays from Pi Imaging that can read out binary frames at 100,000 frames per second. So you can think of these as having like 10 microsecond timestamping capability. So that's the trade-off. It's spatial resolution versus temporal resolution. You can't currently have both, but we tried to emulate what you could do if you did have both in the videos we showed.
And this is an engineering problem, or are there actual physical limits that we're just a few orders of magnitude away from?
I think it's an engineering problem. We need better on-chip compression techniques. I mean, what I'm showing here suggests that you don't need to read out every photon. Maybe you can capture these statistics, like the Fourier coefficients of the signal you're sensing, and then you can get similar information, but with less bandwidth. So in that sense, it's an engineering problem. But if you're trying to read out millions of photon timestamps per second from millions of pixels, that's starting to look like it's outside the realm of possibility, just in terms of data rates and heat dissipation and things like that.
Okay, thanks.
Yeah, good questions.
I don't see any more questions. I have plenty, but I'll save them to the end, just
Yeah.
in the interest of getting through your talk first. So.
Okay. All right, so let's get to the second part here. Okay, so I'm going to switch gears a little bit and talk about how we can extend ultra-fast imaging techniques to 3D reconstruction and view synthesis, and the interesting effects that we see when we do this. So I want to tell you about Einstein's famous thought experiment. So he imagined famously that an observer is standing at a platform and a train is passing by. And at the precise instant that the middle of the passenger car reaches him, 2 bolts of lightning strike both ends of the car, apparently at the same time to the observer on the platform. And then Einstein poses this question: if there's an observer standing in the middle of the passenger car moving with the train, does he or she also see the lightning bolts strike simultaneously? Or do they appear to strike one before the other? So for the observer at rest, both wavefronts arrive to the observer at the same time from the lightning bolts, and so they appear to have struck at the same time. But for an observer moving at relativistic speeds towards one of the wavefronts, if that wavefront will close faster, and the right event in this case will appear to happen first. So one question is if we can capture and visualize light propagation from moving viewpoints like Einstein imagined, and if so, what can we learn about a scene by watching how light propagates through it? So this is a video that we captured, again, with the Coke bottle. We have a picosecond pulsed laser that's coupled to a fiber and out-coupled through a collimator, sends pulses of light through this Coca-Cola bottle. And we capture videos of the scene with a scanned single pixel SPAD. And we can then, using these videos, render what the scene would look like from any viewpoint as the light is propagating through it. And so before I play this video, I'll just ask you to think about, what do you imagine will happen as the light pulse propagates through this Coca-Cola bottle video, through this Coca-Cola bottle? Will you see in the video the light reaching the near corner of this ground plane or the far corner first? Okay, so let's see what happens. So we can see the pulse here entering the Coca-Cola bottle, and we see light refracted through the bottle on the ground. Propagates to the end of the bottle, focuses at the cap, and then light scatters out and appears to reach the near corner first before propagating away from the observer, away from the camera, towards the other side of the scene. And then at about 3 nanoseconds after the event started, the light appears to reach the back of the bottle. I'll play this back one more time. So why do we see the light arrive to the near corner of this this plane first? Well, simply because that's the shortest path length from the bottle to the camera. And so indeed, this would align with what you might expect would happen, and probably aligns with Einstein's intuition. And we can capture and visualize light from moving viewpoints, but we can't capture all the effects that Einstein imagined, in particular because we can't move at relativistic speeds. So the video that I showed you was not captured by moving the camera at the speed of light, but was synthesized using neural rendering techniques after capturing videos of propagating light from multiple viewpoints. If you were to move at relativistic speeds, well, what happens is if you're moving towards a wavefront of light at a significant fraction of the speed of light, you would expect maybe that that wavefront would appear to be closing to you at faster than the speed of light. If you are on the highway driving in your car and another oncoming car is approaching you, you'll see it closing towards you at the sum of your two velocities. But that's not the way that light works. In fact, the speed of light is constant in every reference frame. So what actually happens is that space-time itself constricts ahead of you so that the speed of light is maintained. And that's called Lorentz contraction. So these types of effects are not effects that we can actually observe with this technique, but other effects that depend on the path lengths of light, we can actually see in the videos that I'll show you. So we can't move at relativistic speeds, but we can capture and visualize propagation of light, including some viewpoint-dependent effects. And of course, ultra-fast imaging techniques have been around for a while. I've shown you a few applications of this, but there are many modalities of ultra-fast imaging, including street cameras, time-of-flight cameras, interferometric techniques, and using spats. But previously, they've been limited to single viewpoint capture. So our work is building on techniques for neural radiance fields and view synthesis from videos, but the existing techniques are always operating at conventional imaging speeds in a regime where you don't have to account for the situation where the speed of light is finite to you. You're operating at, and we're operating at sufficient speeds where that's the case. And we're also building on some previous work of ours where we performed view synthesis of LiDAR measurements, but in this case, we're only modeling direct reflections of light. And we'd like to be able to capture rich and complex light transport effects at ultra-fast speeds. So in particular, I'll tell you about our technique for view synthesis from videos of light propagation. We use a new type of neural field, neural network, neural rendering-based approach to make this possible. And we captured a data set, and I'll show you some of the results that we captured. Okay, so how does this work? So we used a setup similar to what I showed you in the first part of the talk, but in this case, we pair the SPAD with some scanning mirrors and a pulsed laser. And we repeat the measurement over and over and do more of the conventional type of high-speed imaging where we capture a histogram of photon counts arriving over time, which we'd also call a transient. And after scanning the entire scene, we get one of those histograms at every single scan point, which gives us a video of light propagating through the scene. And then we repeat this whole procedure for multiple viewpoints, or multiple viewpoints of the scene. We keep the light source fixed with respect to the scene, so it's as if our camera is moving. And we get a whole set of multi-viewpoint videos of light propagating through the scene. And these are interesting to look at. So if I pick out two of these and I zoom in, you'll notice that the light propagation appears different from different viewpoints. So if you look at this left wall here, for example, you'll see the wavefront of light propagating down and to the left. In this right viewpoint, the wavefront appears to propagate straight down the wall. Why is that happening? Well, it's because light transport at these timescales is viewpoint dependent. As the camera is moving, there are different path lengths to every point in the scene. And so the appearance of how light propagates due to these different path length delays also changes. So every camera viewpoint has its own temporal reference frame. And this complicates neural rendering and view synthesis because you can't assume that the appearance of the scene is constant as you move the camera. You have to account for these path length delays. So to do this, we build on conventional neural rendering techniques and neural radiance fields, which position a virtual camera in the scene, position a virtual camera in the scene that you aim to reconstruct, and you cast a ray out from the center of projection of that camera, and you query a neural representation along samples on that ray. And your neural network returns for an input 3D location a density, and conventionally it returns a color value. But in this case, we instead return a per sample transient, which is a one-dimensional waveform that describes the outgoing radiance, outgoing time resolve radiance from that point. So at every sample location, we have a long array, we have one of these one-dimensional waveforms. Now we can explicitly reason about the path length delay from the camera center of projection to every sample along the ray, calculate that delay, and shift these 1D waveforms by that time delay. And after that, we can composite them together using volume rendering, which gives us a transient, a rendered transient for that particular ray, which we can supervise with what we measured. So then this whole representation is optimized to return rendered transients that look like the measured transients. And we can render, after it's been optimized, we can render videos from different camera viewpoints by just performing volume rendering from that viewpoint, moving the camera position, increasing the time bin that we sample from, and rendering a new video frame. And so using this representation, we can perform view synthesis of videos of propagating light. So we did this in practice with a hardware setup. It looks like this. We have this gantry. There's a rotation stage that we mount the scene on. We have the fiber-coupled laser coupled, mounted to this rotation stage that sends pulses of light through the Coca-Cola bottle in this case. And then the SPAD is mounted on an elevation arm. And so we can capture multi-viewpoint videos in this fashion. This is sped up, so you can see the rotation stage turning. The SPAD captures the scene at different elevation angles. So what we end up with is videos captured from different azimuth and elevation angles of the scene. This is a pretty slow process. It takes about 20 minutes to capture a single video, and then you have to repeat that for every viewpoint. So it takes about a day to capture the full data set. Okay, and what do we end up with? So I'll show you first just some simulated results. So by capturing a transient video, you can see all sorts of interesting light transport effects. You have wavefronts propagating, in this case, from a point source, and that are incident on the scene. You can see refraction through this glass ball in this particular scene, and indirect light transport effects, light that scatters multiple times in the scene. And we visualize these results by compositing the integrated image, or an intensity image, on top of the transient video, just to get a better idea. We find this gives you a better idea, more intuitive to see what's happening in the scene. And we can compare our reconstruction to previous approaches. So in particular, we can compare to transient NERF, which is our previous work that only models direct reflections of light. And in this case, we see more artifacts in the reconstruction, particularly where we expect indirect light, or light to be scattering multiple times. We can also compare it to techniques for video view synthesis. This is a technique called K-planes that doesn't account for propagation delays of light, and so struggles to perform view synthesis because the appearance of the scene changes with different viewpoints. And our proposed technique is on the right, which gives you a much cleaner reconstruction, similar to to the ground truth render that I showed on the previous slide. And so let's see what this looks like on captured data. This is a scene that we captured that has a mirror, a statue, some other objects, and we illuminate it with a point source. So what's interesting here is that as we move the camera, the wavefront propagating through the scene on the left appears frozen, because the camera is basically moving in the direction of propagation, which results in that wavefront freezing. Light reaches the statue before you see the reflection in the mirror, because the it takes light a longer amount of time to propagate to the mirror, reflect back to the camera. And then you can see other light transport effects in indirect lighting, such as light reflection, specular reflection off of this magazine cover. Here's a scene that we captured by putting a mirror and a diffuse reflector into a tank of water. And then we put a little bit of milk into the tank so that some of the light would scatter out to the camera. And you could see so you can see the light as it propagates through the water. And this is what we get. So you can see the pulse propagating through the water, specular reflection off of the mirror. And what's interesting here is as you move the video camera behind the pulse, if it's propagating away from you, it appears to be dimmer. So why does the brightness of the pulse depend on the angle that you view it from? Well, this is basically the phase function of the water with a bit of milk in it. Turns out that that's predominantly forward scattering. So most of the light scatters in the forward direction, less light scatters in the backwards direction. So the pulse looks dimmer when viewed from behind. And then you can see the diffuse reflection and scattering out of the tank. Here's one more example in the water tank. In this case, we put a diffraction grating, and you can see the pulse of light being split into its, well, you can see the 0th order mode, first, second, and even partially make out the higher order modes coming out of this diffraction grating. And then just one more example. This is a scene where we have a couple candles. And what's interesting about candles is that they have a lot of subsurface scattering. So most of the apparent brightness of the candle is from light that scatters through the surface, propagates into the surface, scatters around for a while, and then leaks out over time. And you can see these indirect light transport effects in the videos that we render. So you can see how the candle appears to glow for a little while due to all the subsurface scattering. And then we can see some interesting indirect light transport effects and multiple scattering of light through the scene. Okay, so we hopefully have convinced you that we can actually capture and visualize light propagation from moving viewpoints. In some fashion, perhaps as Einstein imagined. Of course, we can't capture relativistic effects, but we also did try to simulate some relativistic effects based on the data that we captured, and we show some of that in the paper. This was at ECCV last year. So this gets to the second question. What can we learn about a scene by watching how light propagates through it? So what we've been working on more recently is to develop physically based inverse rendering techniques that operate on videos of propagating light. And if you can model using inverse rendering indirect reflections and multiple scattering of light, one thing that this allows you to do is to recover scene geometry far more accurately than techniques that only consider direct reflections of light. We can also perform relighting. So you can use the same data that I just showed you, apply physically based inverse rendering, and then relight the scene from different positions of the light source to see how light, in that case, would interact with the scene. So each of these wavefronts, the red and green and blue light, are illuminating the scene from novel light source positions. We can also automatically separate light into its direct and indirect components. So in this case, you can see, for example, that the candles appear much darker than in the indirect case, and you can see in the indirect component, especially around corner geometries, indirect reflections of light. This is maybe more clear in this scene, where we can, again, recover geometry or surface normals and split light up into its direct and indirect components. And here's another example of relighting and splitting up the direct and indirect light from not rendering the scene with novel light source positions. So I think this is just the beginning of, we've just only begun to explore what you can capture, what information you can glean out of these time-resolved videos of light propagation. I think you could probably improve the geometry that you estimate and also make more use of indirect light, for example, light that scatters behind occluded regions of the scene, and perhaps you can recover those directly. It's possible to recover material properties of a scene by decomposing the light transport, and there may be other applications. So in particular, our current model doesn't handle participating media, our model for physically based inverse rendering. And so extending this to be able to see through murky water or fog, I think would be really interesting. See through tissue, seeing through tissue might open up applications in biomedical imaging. This could be relevant to non-line of sight imaging or other modalities that maybe you can improve LiDAR or recover, maybe you can improve higher level vision algorithms that try to do segmentation based on material properties. And we're also, recently we've been exploring how we can apply generative modeling techniques to low light imaging and single photon imaging. So in that vein, you can compare what you capture with a conventional camera to the binary frames that you capture with a single photon camera. So these are frames that we captured with our 1/4 megapixel SPAD array. The pixel, if there's a pixel value of 1 in the binary image, that indicates that you detected a photon during a 10 microsecond exposure period corresponding to that frame. If the pixel value is 0, it means you didn't detect a photon. And of course, and so in this case, what you'd like to do is come up with some probabilistic model that tells you the probability of the clean image given the photons that you observe. And if you have a shorter exposure time, or the light conditions are, or you have less light, you could still perhaps try to recover an estimate of the most likely clean image given the photons that you observe. And I think that this sort of technique is possible given that unconditional generation of images or videos is now working really well. So these are some results of one of my students who's been working on video generation. And you can, in this case, control the camera viewpoint in the generated video. So you can generate the same scene over and over again with from different camera positions. And basically, there are entire 3D or 4D scenes living in these models that you can generate and extract. And so if we can do this, I think we can certainly apply these models to inverse problems such as single photon imaging. We've done a bit of this. So you can see, in this case, this is simulated photon detections from this scene in the center column. And the right column is a generated image, which gives us an estimate of a clean image from the photons that we observe. So this could maybe be useful if you're maybe not so interested in like the texture. Is this building made of brick or some other type of stone? Or you know, does the pavement look exactly like this? But maybe you have a robot that needs to navigate in low light, and you just need to, you'd like to create clean images that have roughly the right semantic content, can identify the navigable area of the road, and are compatible with your downstream vision applications. And so perhaps generative models can bridge noisy photon detections in low light to these downstream applications and enable these applications to work robustly in low light conditions. Okay, and so those are just a few directions that we're excited about for future work. And overall, coming back to the theme of the talk, and imaging from seconds to picoseconds, I think there's really a whole frontier of ultra-fast imaging across timescales that we could also explore. Are there phenomena that we cannot conventionally observe simultaneously that are maybe correlated in interesting ways? And perhaps it would even be interesting to think of imaging beyond seconds to picoseconds. And what can we observe, for example, as we push to faster and faster timescales? And perhaps that's even possible now with attosecond lasers. So I'll leave you with that. I'd also like to recognize collaborators on this work, in particular Anag, who's the student leading view synthesis project, rendering views of propagating light, Mian Sotiris, who are leading our work on passive ultra-wideband with Kyros Koutalakos at University of Toronto, and also collaborating with Gordon Wetstein and all the other students working in these directions on the group. And yeah, I'll leave it at that. Thanks very much.